All right.
This is, and then this is.
There we go. Looks good. And the big button,
I got it.
the big one advances the
That
slides.
advances. Get closer. Are we?
Oh, did I do that wrong?
Can we full screen?
Sorry.
Oh, yeah.
Ah, thanks. Great. All right. So next we have,
Oh, maybe hit the green.
there we go. Okay, great. Next we have Christopher Mendillo, who's going to tell us about the first results from Picture D, first flight.
Thanks. Hi, everybody. So in 2006, as a second-year grad student, I started working on a mission called Picture. I didn't know that I would spend the next 20 years also working on a mission called Picture. So in 2026, here we are. We have flown 5 missions now, direct imaging coronagraph missions with AO and BMC, MEMS deformable mirrors in or near space on 2 sounding rockets and 3 suborbital high-altitude balloons. So I'm here to tell you about the latest iteration called Picture D. This is an image of Picture D floating in the stratosphere 130,000 feet over our heads in New Mexico. It's about roughly 40 kilometers. It's a mission sponsored by NASA, built in the basement of one of the oldest textile mills in America in Lowell, Massachusetts, on the UMass Lowell campus. And it's a mission to do direct imaging of, we hope, debris disks around nearby stars. So this is Picture, we'll start with a quick recap of the balloon part at least. Picture C, which is the original one. We flew this twice, in 2019 and 2020. This is our gondola. It's about 15 feet long. It weighs 6,000 pounds. The telescope which we build, which is the inner truss there, is about 1,500 pounds. That's what we build in our lab. We ship it to to Virginia. It gets integrated with this pointing system, which is called WASP. That stands for Wallops Arc-Second Pointer. It's been pioneered by a great group of engineers at Wallops Flight Facility. Okay, so now Picture D is the same thing with a lot of new upgrades and a lot of new partners. The main upgrades for this mission are we've added a second deformable mirror to do a symmetric dark zone. We are integrating photon counting science detectors that are very similar to the ones on Roman coronagraph. We are attempting to integrate a grating vortex or a scalar vortex to be able to do simultaneous dual polarization imaging simultaneously. And we are trying to do a demo of multi-star wavefront control and dark zone maintenance on the sky. Okay, we have a big group. Our group keeps growing and growing and growing. We have a great team of undergrads and postdocs at UMass Lowell, and a lot more external contributors now, many of whom are in this room right now, so big thanks to all of you. And so let's get into the description of the mission. This is the side view of Picture telescope. We have an off-axis 60-centimeter primary mirror, an actively controlled hexapod that controls our secondary mirror position. The whole truss is made out of aluminum. At that altitude, the ambient temperature is minus 40 degrees C, so the entire telescope shrinks by about 3 millimeters. We need to maintain micron level alignment of the secondary mirror, so we have a hexapod out front. We have an off-axis coronagraph that's a vector vortex coronagraph, and you'll see a lot more about what else is in there. On the back end is all the electronics and counterweights that balance us inside the pointing system. So quick recap on Picture C. This was the previous iteration of the coronagraph that we flew. This is the optical bench showing the light path that comes through. Does this work? There we go. We have a low-order DM that does fast tip tilt and low-order Zernike correction that's fed by 2 wavefront sensors. We have a Shack-Hartman low-order wavefront sensor that does telescope alignment and overall focusing of the PSF. And then we have a LOFIS down here that's a reflective Leo stop that Sebastian now tells me is called a YOFIS, because in Chile they call it a YOFIS, because it's LL. Thank you, Sebastian. I wanted to get that in there. I just learned that 10 minutes ago. So from now on, I'm calling it YOFIS. Okay. We have a vector vortex chronograph over here, a bunch of OAPs that fold the beam around. In the first iteration, we had this integrated controller for the BMC mirror. This is a kilo DM. We had the LPO low order tip tilt, and it can do like 20 to 30 Zernicke's stabilization. Okay? Okay, this is it integrated with WASP. We brought it down to New Mexico twice. We flew it. This is 5 a.m. Yeah, this is the first flight, the first time we flew it. Okay, you go to this municipal airport that's been now commandeered by NASA to fly these balloon missions in Fort Sumner, New Mexico. So in the first flight, mostly, everything worked very well. We didn't do any high contrast stuff yet or high order wavefront control yet. We did low order wavefront control. So up here you can see the low order, the reflective LEO stop. And I'm on the ground sending commands to close the loop on all the Zernikeys as we go up the chain, so you can see them getting stabilized as we go. We flew the high order DM off the side of the bench just to make sure the controller and everything didn't break. Okay. We flew again in 2022. This flight was a bit more successful. We had the full AO system running. We flew for 18 hours. We looked at 5 different stars. We landed in the middle of the desert in a nice soft patch of pasture. Okay? And we did a demo of the first flight dark hole. So the first dark hole ever dug in a coronagraph that wasn't bolted to the surface of the ground, or onto a telescope on the ground. We didn't break any contrast records, but we did get to 5 times 10 to the minus 6. You can see on the bottom panel here, whoa, I don't know how to go back. Okay, there we go. That we were able to clear off with a single DM the right side of the image. Okay? And we also did very, very high precision stabilization of pointing and low order Zernikeys. Up here you can see this is the power spectrum in pitch and yaw and the time series down here. The blue line is what the telescope is doing. The black line is the stabilization inside the instrument. We're hitting 1 milliarc second RMS pointing in pitch and yaw. Okay, this is a record for us. This is on a balloon, on a telescope that's on a 1,000-foot long cable below a balloon that's swinging in 1G. So that's pretty cool. Big issue from the second flight is that this is flight 1 on top and flight 2 on the bottom. This is just pitch. We had all these we call them pings, these little transient pointing in the black line, these little pings that keep popping up. And every time one of those would kick off, it would shoot the star off the chronograph, and then it would come back in, but it would completely destroy our ability to do EFC. So I missed the SPIE in August because I was down in Wallops trying to figure out what was going on. We did a bunch of hang tests with the telescope. The reason I had to go to Wallops is because only the PI is allowed to hit the payload with a hammer in order to test what's going wrong with the payload. We had thought it was coming from the cables, all the bridles that come down to the gondola, but you can sit there and whack it with a hammer and the pointing system doesn't even see it. So we proved that it wasn't that, and actually we figured out it was something to do with the friction inside the pointing motors, and they were able to fix it, and we didn't see it at all in the most recent flight. So that's some great news. Okay, on to picture D. Okay, I told you everything about that already. Here's our new chronograph bench. It's the same bench. We just redesigned the optical layout. We've added 2 high-order DMs. We are not using an integrated controller anymore, which is a bit of a bummer, because now we have 2,000 wires coming out of our DMs. I'll show you a picture of that in a second. We have these nice flex circuit interconnects that come off the back of the DMs and go off to these side panels where all the cables plug in. We have same vortex. We've greatly increased the F number on the vortex, which helps a lot. We've added a beam splitter here to split off some of the light. Oh, this is weird. To a pupil imaging camera. I'll show you an image of that in a minute. But then other than that, it's the same basic idea. Yeah, nothing else too new here. Okay? So here we go. We have dual 952 channel BMC MEMS DMs mounted about 18 inches apart on the bench. And these flex circuits that go up over the top, over the side. Here we are putting the whole thing together. You can see all the flex cables coming over to the side here, and then getting plugged into these ribbon cables that go along the side of the coronagraph and back to the controller. Here we are integrating the coronagraph with the rest of the telescope. We did a lot of this work in a new clean room that we built in the lab next to our existing lab. That was sponsored by Roman Technology Fellowship that came along at the start of this mission. Okay, here are all the DM cables going from the controller on the back end. This is a Telich 2K controller, so we're using one controller to control 2 kilo DMs, okay? 2,000 wires coming out of that, going around and back and into the side of the chronograph. So one implication, obviously, when I see this is for HWO, we're talking about 10 times as many, 20,000 wires, okay? We have to all think about how challenging it is going to be to get that many wires. into the coronagraph. The other interesting thing about this picture is that the day after I took this picture, I came into the lab to do some final testing before we shipped, and one of the DM actuators broke. And we went, oh no. And it took us, okay, so it took us a little bit, but we figured out DMs were fine. A controller channel burnt out, which is very strange. A single channel burnt out. We went back to all our connection mapping database and figured out that there was one other cable that if we swapped the two cables, we would get that actuator back. We did that. We're back to 100%. Okay. Really nice picture of the power supply that we built for this. We have this new, we have a new staff electrical engineer on the team, and his first job was to design and build a new flight power supply, so I wanted to recognize his work. It's a very nice system that allows us full control over all our power buses from the ground. Okay, so this is on the ground. This is not in flight. This is an image of our GSE interface, and this shows everything that we're doing sort of simultaneously. We have our Shack-Hartman wavefront sensor image over here, the reflective Leo stop over here, low order DM command over here, the two high order DMs are over here. We have the pupil camera over here. We have the measured raw contrast, instantaneous raw contrast over here, and then the estimated field contrast over here. You probably can't see the numbers. This says 6 times 10 to the minus 7. This says about 4 times 10 to the minus 7. We have a planet right there. This is a ghost image from something. We don't know exactly where it's coming from, but it's very handy for calibration. And you can see it's not in the coherent field measurement over here. Okay? What else to say? That's that. Here's the pupil camera. So in flight, we operated this. And so what you're seeing here is an animation of me poking up a registration pattern on the two different DMs. They're in two different planes, right? So the more faint one is the first DM, which is in a pupil. The brighter or darker ones you're seeing is from the second DM. And that lets us make sure that the beam hasn't shifted on the DMs. Okay, another cool demo we did, this was in New Mexico. Susan Redmond and Christina Page were both there, and Leonid helped a lot with all this work. We ran a DZM, a dark zone maintenance routine. We had it already implemented, but they came and we had like 2 weeks of downtime waiting for the weather. So we, of course, we're going to start messing with the flight code, and we go in and we added this 3-state DZM routine that does maintenance of the dark zone. So the green line on the right there is what the dark zone would be drifting to, and the black line is what we're controlling it to or maintaining it. All right, let me get to the launch. Okay, 2025, we launched. Here we are. We got Carl, we've got Ananya Sahu, we've got, here we go. Oh no, I pushed the wrong button. Oh, I got so many things to show. Okay, Susan and Christina, myself, and a postdoc, Sunip Mukherjee. It took us 9 times to launch. 9 attempts to launch. We finally launched on October 1st, which you may remember was the first day the government shut down, which was also a big bummer, and we almost did not get off the ground. No time to talk about that now. I want to show a video of us launching. I don't know if there's sound. I guess not. Oh, there is. Cool. Okay. You will hear. Okay, so they let the balloon go. There's a guy named Larry driving this big truck. Larry sees immediately that the balloon is going that way instead of this way. So he takes the truck and starts driving. And if you hear him start screaming, there are a bunch of people watching over here. I probably should, hold on, listen. Someone's screaming. Okay. There's a bunch of vehicles over here. Okay, I probably shouldn't be telling you all this stuff, but you hear someone scream, run! Okay, it's not supposed to go that way, but you know, we're in a shutdown. No one was watching. Okay. Okay. We get off. Great. We got off the pin. Really cool. All right. This is a really cool flight animation that one of my undergrads built. So this, we were live streaming on YouTube. This is showing the entire mission of the experiment's point of view. So all the different stars we were looking at. I'll kind of fast forward through here, but you can kind of see our entire mission in fast forward here, okay? This is a video of the same kind of look. This is sped up 60 times so you can see inertially what's happening. The gondola is going like this. The telescope is maintaining an inertial pointing. So there's a lot of dynamics to deal with. Okay, we did astronomy for the first time. Whew. It's not amazing astronomy, but we did one unit of astronomy. We took an image of a binary star system, not a huge contrast, okay? This is okay. This is gamma Cas A and B. It's about a factor of 3,000 in brightness between the two companions. This is a similar image from Keck on the right. Yeah, so this is a single frame, single 8-second frame taken during the day with a lot of sky background. We have an hour of this data. I have a student trying to reduce it to see if we can recover an image of the C binary companion, which should be somewhere around here. I don't think that's just a speckle, but it might be in there. All right. Okay, so that was the good news. This is the bad news. We didn't do very well with high contrast imaging. This is what I like to call a menagerie of failed dark zones. Okay, I gotta go. All right, big thanks to Carl and Susan, who were in the room watching me go, why isn't it working? The entire time, because we had a lot of issues, mainly due to throughput with our instrument. You can ask me offline about that. We had to lower throughput on our tracking camera that made us have to slow down the tracking, which meant we couldn't stabilize very well. This is images from the sky of 3 different stars and simulations. I can show these in log space to show that the PSF of our nice unobscured telescope looks exactly the way we expect it to. This is the tracking camera. All I'll say about this is that in flight, it was about 20 times dimmer than we thought it should have been. Okay, not great. Okay, at midnight, we decided to wait for the brightest star in the sky. I'll finish up. To rise, Sirius, but then our battery died at 12:40 in the morning. Lots to say about that, but no time to. Then this happened. So we all went home. We got just enough time to safe the instrument and shut it down and then go home, and we wake up the next morning to all these headlines because apparently we landed in somebody's farm in the morning, so someone actually has a cell phone camera of our payload landing on a parachute, which is amazing. We didn't crash. We did trend on TikTok for a little while. Very cool. All right, last slide. What worked? Basically, everything worked except the high-speed LOFUS was too dim and the battery died. We're going to do much better next time, I hope. We're trying to get a launch off at the end of this year if we can. This is a photo Carl took from the ground of our payload and the fully inflated balloon at 130,000 feet. I'll stop there.
Unfortunately, we don't have time for questions, but please reach out if you have any more questions, and we'll get the last speaker up here. No problem. Very exciting stuff.